All right, so last two class periods we started working with fractions. Last time, what operations were we working with? Addition and subtraction, and today we're going to work with multiplication and division, okay? So we're going to look at multiplication and division of rational numbers, particularly fractions. All right, so we've got two numbers, a over b and c over d, and we're going to talk about what it means or looks like to multiply them together. So just as far as a definition, what we do is we multiply across the top, we multiply across the bottom. You guys remember this, right? Okay. I want to show a rectangular diagram of how that works and why. So the two numbers we're going to work with are going to be 3/5 and 3/4, and we're going to multiply them together. So you know by the definition above and by previous work, the answer is going to be what? 9/20. So I'm going to show you a picture that's a rectangular region that will illustrate this working. So we're going to take a rectangle. And if I can draw well enough, I'm going to split the rectangle, and it doesn't matter which way I do it. I'll use 3/5 first, into 5 columns. Okay, and again, if I've done it well enough, then they should look like they're equal. No guarantees on that part. Too bad. Okay, and then we're going to shade in how much? What would represent 3/5? 3 of them. So we're going to take, I'm going to try this. Like that. So there's 3/5 of them shaded, right? Okay, the next thing I'm going to do is I'm going to take the same rectangle and imagine no, there's no shading. Okay, picture it empty. It's not. Picture it empty. We're going to divide it into fourths, but we're going to do it horizontally, so 4 rows. Okay? And I need to shade in how many of those 4 rows? 3. Looking for a little bit more transparency on those. Let's do it this way then. Okay, so all right, so the question is, what part of that picture is double shaded? 9 of them, right? 9 pieces. How many pieces total? 20. Okay. So 9/20 of this gets double shaded. Now, one way to image or to picture this happening is to sort of ignore this piece over here. So ignore that this is here. So it's not right there. Okay. You're just looking at the right-hand side. Okay. The part that was actually shaded over there. And if you divided this into 4 pieces, it would still have the same 4 pieces. These aren't here. Okay, and you would say, okay, there's 9 pieces there shaded, right? Period, shaded. That are, with the red on there. 9 of those are shaded. But the reality is that each one of these boxes, kind of like the one that Morgan we were talking about that had the 12ths, right? There's size was 12, the size was 1/4. Each of these are size 1/20 in the boxes because the unit itself, right, is the big rectangle. It's a sheet cake, like cake, right? So we've got each piece is size 1/20, and we've got 9 of them that were classified. So this is a picture diagram of where that 9/20 comes from. All right, so we're going to look at some properties of multiplication next. The first property, and Again, for those of you who've gone through Math 1, some of these properties are the same. There's a few that are different, but the first one is the same. We have an identity property. So there's an identity element of the number 1, such that if you multiply the number 1 by any fraction, it's still equal to the fraction that it was before. Right? You guys know that about the number 1, right? It's called an identity. We also have, and this is something new that we have, we did not have these for any other number systems until you get to the rational numbers. You have inverses. So if you have the number a over b, and you flip it upside down, b over a, that is called the unique inverse element. And what it means to be an inverse is it means that when you multiply a number and it's inversed by one another, you get back the number 1. And according to our property that we had before here, that's exactly what we get. We get a times b, this is b times a, and those are the same quantity, right? It's called commutative property of multiplication. So a over b, another a over b, and if I divide something by itself, it's the value 1. This is an inverse property. All right, so the next one is the distributive property. The distributive property works the same no matter whether you have whole numbers or integers, or in this case, rational numbers. If you have a number and it's being multiplied over, or at least through, or however you want to describe it, through a set of parentheses, you can actually draw arrows in this way, and it means this a over b would get multiplied by the first fraction c over d. We would add to that a over b times the second fraction e over f. Same distributive property, in other words, hey, that old distributive property, you know, it works for fractions too. Okay. Property of equality, again, same kind of thing. Property of equality says that if we have two numbers, a over b and c over d, and they're equal to one another, we use this for equations, right? If you have two sides of an equation and somebody says they're equal, then as long as you multiply both sides of the equation by the same number, the equation remains equal on both sides. Okay? So, thinking back to our example of our book, if I had 2/4 and 1/2, right? Those are different numbers, but they have the same value. And I multiply each of them by 3 over 7, they're still equal to one another. And that's what this is saying. All right, property of inequality. All right, so this has to do with using those inequality symbols. So we're doing the same thing as we did on the last slide. We're multiplying both sides of an inequality by a number, e over f. Okay, so we've got some value. We multiply by e over f on the same view of both sides. Here's the deal. This tells you that if your value you're multiplying is positive, okay, so if this one has a greater than symbol and you're multiplying by a positive number, that when you multiply on both sides by that positive number, you still have the same symbol. It's still the greater than symbol. Okay? So if I talk about 1/2 and 1/4. 1/2 over here, it's bigger than 1/4, right? So, what am I doing? Miranda. So if Miranda has 1/2 of a pie, and is it Grant?
Yeah.
And Grant has 1/4 of a pie, then Miranda has more than Grant, right? If we then took the pie and we multiplied it by 3, I know it's not a rational number, well, it is a rational number, it's a whole number, but bear with me. So if I gave you 3 halves of pies and I gave you 3/4 of pies, you still have more. Right? That's what this is saying. The second one's saying something else. What's the issue here? It's negative. So you remember from somewhere in elementary school, when you were working with fractions for the first time, maybe about 5th grade or 6th grade, and you're working with inequalities, somebody said, that's all well and good unless you multiply or divide by a negative. When you multiply or divide by a negative, it changes the direction of the inequality. It changes the sign. Greater than sign becomes a less than sign. Okay? That's what this is talking about. And I want to show you what happens with this because it sort of looks like, okay, that's a rule, but it doesn't really make sense without an example. So let me use that same 1/2 and 1/4 as before, and let's just multiply by a -3 now, okay? So let's say we multiply both sides by -3. This is now -3/4. This is now -3/2. Okay, so ignore the negative. If it didn't have the negative, which of those is bigger? The 3/2. So the -3/2 is a bigger negative number. but a bigger negative number is a smaller number. So this inequality changed, and you can think about sort of doing this, if it helps you, you can do it in terms of decimals. So this is negative 1.5, this is negative 0.75. So thinking along a number line, here's negative 1.5 and here's negative 0.75. So it is in fact going to get smaller because it's further to the left of the number 1. So that's what's happening there when we multiply by negatives. And then the last property we're taking a look at today is, or at least in this section, is the property of 0. So if you multiply by 0, what happens? You get 0. And it doesn't matter what that number was, you multiply or you took 0. So this is a multiplication property of 0. We're going to do an example of these. All right, so we're going to solve the equation. At every step of our equation that we solve, we're going to justify by one of the properties that we just talked about. Okay, so what would you like to do? There's several things you could do. Somebody give me an example. What would you like to do first? You're going to divide? What do you want to divide? You're going to divide by 3/4? Is there a different way of doing division? What can we multiply by? Okay, let's do the multiply by 4/3. Anytime I'm dealing with fractions, I kind of don't like division. Why would I want to use 4/3? Okay, what is 4/3 in respect to 3/4? It is the inverse, and it's going to make it 1. So I'm doing this because this is the additive inverse. And when I do this, I'm actually going to get, I know that you don't want to see me write this, but I'm going to do it anyway. I'm going to get 1x. That's really what I'm going to get. I'm going to get 4/3 times 3/4. That's actually the number 1. So I'm going to actually get 1x on the left. What do I get on the right? What is 1/5 times 5/3? 4/15. Now, what you guys wanted me to write on the left was just x. Why is that the case? It's the additive property because if we divide by 1, we still have 1 divided by 1 is 1. So it's not going to make it go away. But it's because it's an identity. So this step right here where this becomes, where 1x becomes just x, is the identity property. So, and we used additive, and that was so not the right word. That was my fault. I did it, not you. What word should I have used? Thank you. Somebody said it. It's the multiplicative or multiplication. Multiplicative inverse. This is the multiplicative identity. So the multiplicative inverse and the multiplicative identity allow us to do both of those things. And you typically don't write them in different steps because you guys have sort of gotten to the point where you get this is okay, right? Okay, we're going to do another problem, same idea, but there's more to this one because what do you see? Couple x's. What else? Addition, subtraction. Somebody bothered by the multiple different denominators? Oh, we got that too going on, don't we? Okay, so I'm going to suggest doing something maybe a little bit different. I don't know. You guys don't have to like it, but you may not have seen it, so I want to make sure you've seen something like this before. One of the things that you do often when you're trying to work with fractions is you try to get a common denominator, right? So let's get a common denominator right now to start. Are you okay? All right, so we've got 3, 4, 6, and 2. We're going to use 12. All right, so let's start with getting a common denominator. So we're going to multiply the first one by what? 4 over 4. What about the second one? 3 over 3. The third one? 2 over 2. And the last one? 6 over 6. All right, so what does the first one become? 8x over 12. The second one? 3 over 12. The third one? 2x over 12. And the last one? 6 over 12. Okay, so that's going to fix the issue of all the different denominators for us. So So at least when I start moving things around, I can combine them already. So what would you like to do next? Okay, Kayla, give me one of the things you want to do. We're going to do one at a time. Give me one. What do you want to add? Add which one? Megan, what's the 6/12? Okay, so why am I allowed to add 6/12 to both sides? Okay, it'll keep it equal, that's a property, you're right. So the additive property of equality, and the reason I want to use that one, Marissa was saying, is because it's an additive inverse, right? It cancels it out of equals 0. Okay, so there's two things going on. This is the additive property of equality. That's what allows me to do it. I forget, I actually failed to mention that on the previous slide. That's what was allowing us to do this too. This is the additive, not additive, multiplicative property of equality. That's what actually allows me to do something on both sides with an equal sign. Okay. So this one was the additive property of equality, and the reason we chose to add the 6/12 is because what this is going to do is this is going to become 0 over here. And that right there is the additive inverse. Okay, so I've got 8x over 12. What is 3/12 plus 6/12? 9/12, and this equals 2x over 12 plus 0. Again, I know you don't like me to write the plus 0. I don't like to write either, really. The point is that it became 0 because it's an additive inverse. And then the right-hand side is going to become 2x over 12 because why? What property leads me from here to here? No, that's with multiplication. That was from last time, actually. The additive inverse. Inverse isn't the right word. Identity is the right word. Right? 0 is the additive identity. It's the number we can add to any number and not change it. Isn't it? That's the additive identity. Okay. I still have 8x over 12 plus 9/12 on the left. Now what? What do you want to subtract, Caitlin? Okay. Minus 8x over 12. And in doing so, we've got the same properties we just did, right? This is the additive property of equality. And this is the additive inverse. And we're going to have the additive identity as well by the time that 0 goes away. So that the left-hand side will simply become 9/12. What does the right-hand side become? Negative 6x over 12. Now what? Say again. What are we doing to the division? Multiply. Let's do the multiply. Multiply by negative 12 over 6, right? Why would we want to do that? Okay, so why does 12 over 6 do that?
Because the multiplication inverse.
Okay, so we're allowed to multiply because it's a multiplicative property of equality. We choose the 12 over 6 because that is the multiplicative what? Inverse. And when I do that, I'm going to get a 1x on the right. What do I get on the left? Make it easy on yourself. Okay, so yeah, good. I think everybody's seeing that. The negatives are going to, or not the negatives, the 12s are going to reduce. It's a diagonal, right? And then I've got negatives still. 9/6. What does 1x become? This becomes x, that's the multiplicative, what? Identity, multiplicative identity. Right, that's what 1 is. And the left-hand side reduces to what? -3/2, because they're both divisible by 2. Right? So make sure that you're including all those steps of all those properties that are happening. They're all happening here, whether you write them down precisely word by word or not, they're all there. So all those properties need to be listed as being there. Okay, that's multiplication. How about division? All right, we're going to do division of rational numbers. There's a couple of things about division I'm going to show you. By definition, division is the opposite of multiplication, right? And that's how we describe it. In fact, that's a lot of times how we teach it. Right? So when I talk to my daughter about what is 6 divided by 2, sometimes I'll turn it around and I will ask her 2 times what equals 6. You ever heard that before? Okay. That's what this definition is describing. This is saying that if A over B is divided by C over D, this is going to equal E over F. If you can turn it around by saying E over F times the C over D, right? You see this? Is equal to the original A over B. It's turning the multiplication description into, sorry, the division description into multiplication, which we have a better grasp on because we've learned it first, is the idea. All right, so our algorithm for division of fractions looks like this, though. So what happens from the left-hand side to the right-hand side of this fraction?
Same change.
Or this equality. What was that? Warren, did you want to say it? All right, so the fraction flips, right? You may have heard the phrase invert and multiply. But why? Why does it work? Well, it has to do with the fact that the multiplicative inverse of something is its reciprocal, right? And that's actually the right word, is reciprocal, where we flip the fraction upside down, not flip. But we use that sort of language. So I want to show you why this works, written out a little bit more technically, I guess. So what A over B divided by C over D actually means is that we have A over B divided by C over D. If you really like fractions, you'll love that one. A fraction inside of a fraction. All right, so one of the things that you have done in algebra, this isn't something you would show to your third grader. Okay, I'm not trying to indicate that it is, but I want you to understand what's happening. One of the things that you've done in algebra is you've encountered things that look really weird like this. Okay? Algebra 2 is usually where you encounter something that looks a little oddball. They're actually called complex fractions. And one of the things you learn to do is you learn to simplify them so that they are back into a form where it's a standard one value on top, one value on bottom. There's not multiple denominators. So one thing I can do then to make that happen is I can multiply by whatever this denominator is. Upside down. I'm not done writing yet, but do you see why I would like to do that? Because that would make the whole denominator, the big denominator, 1, right? But if I multiply by d over c down here, I have to multiply by d over c up here. So like I said, I like that because it gives me a 1 on bottom, but if you'll notice on top I have the a over b times d over c, that these directions over here, or this description of this algorithm, or whatever you want to call it, that I should have ended up with. And of course, division by 1 does not change the value. So this is a over b times d over c. So that's why. Okay. Can I move to the next one? Okay, so I want to describe physically what is meant to divide by a fraction. But in order to describe that, I want to go back to division of whole numbers. If you talk about 6 divided by 2, how could you draw a picture that would represent 6 divided by 2? Somebody give me an example. I'm going to use discs. So if I have 6 discs, 6 cookies, 6 cakes, whatever you want them to be, what could you do to show me what 6 divided by 2 looks like? What could you do? Two groups. That's one way to do it. Okay, so this is make 2 groups. Now, if we have that description in our mind, it becomes very difficult to talk about 6 divided by 1/2. How do I make 1/2 groups? Kind of extend it, but it's not very helpful. So consider doing this instead. Okay, that wasn't so smooth. Doing 2 groups, I could do groups of size 2. How many groups do I have then? 3. So the answer ends up being 3, but it's a very different sort of picture. It's the idea of doing this. There's 2 different ways in a class that I could form groups. I could decide I want 2 per group. This is what I usually do, 2 per group, and then I create groups of 2 people, right? And then at the very end, I have to decide, do I have an even number or an odd number to end up working out or whatever, okay? The other way you can create groups in a class, and you have your teachers do this before, is where you number off, right? When you number off, what you're doing is you're determining how many groups you want to have. Because that's how many numbers I pick. So if you number off by 5, I'll have 5 groups when I'm done. But if I want 5 people in a group, then I don't know how many groups I have when I'm done. See the 2 differences? The reason the second one works really well for this is because it lends itself well to the idea of division. So let's say that I have these same 6 pieces and I want to divide by 1/2. Instead of saying to myself, how do I make half a group? Which would be this kind of a language. What I can do is I can say how many groups of size 1/2 do I have? In other words, how many 1/2 do I have? And if you can imagine taking your picture and imagine that these are something that aren't like coins, because I want to cut the coin in half. Imagine they're cookies. And I divide them in half. How many halves do I have? 12. So instead of creating a half of a group, I'm creating groups of size 1/2. Okay? So I have 12 groups of size 1/2. And so 6 divided by 1/2 is 12. When you divide by a fraction, you get more than you started with. At least a fraction smaller than 1. Okay? So this is what I would do if I were trying to take 6 cookies, turn them into halves of cookies, and figure out how many kids now get a half of a cookie. And I get 12 of them, right? Okay. Along with the idea of multiplication is the idea of exponents in this section. Multiplication and exponents are actually very similar. I want to first just go through the properties of exponents, and then I'm going to justify for you on the next few slides why those properties actually work. So you guys can help me if you remember. What in the world happens when you have a to the n times a to the n? You add the exponents. So what happens when you divide them? Subtract the exponents. What happens when you have an exponent raised to an exponent? You multiply the exponents. All right, these other three. What happens when you have two values raised to an exponent? Two values that are multiplied. That allows you to distribute. And what about when you have a fraction that's raised to an exponent? Yeah, it's like distributing again, right? We're distributing to the top and to the bottom. Okay, so on this one, we will have the distribution as well. But do you remember what happens with negative exponents? Say it loudly. You flip it, right? When you have a negative on an exponent, it flips a fraction upside down. So number 6, actually, the b becomes on top, the a turns to being on bottom, and they both have the same exponent m. Not negative anymore because I flipped it. That's what we get. So I think I would be a terrible math teacher if I let you believe that that was magic, because none of it is. So I'm going to show you why each of those work, and I'm going to do it with some examples. Okay, are you ready? All right, so the first one, the property that you remember says that this should be adding those exponents together. So let me talk about why. We'll do that in a minute, actually, fill them in. You could, but. So what does a cubed mean? What does a to the 4th mean? Count for me. How many a's did you have? 7. So how do you get from 3 and 4 to a to the 7th? You add the exponents. So that's why. Okay, we can do the same thing down here. What is a to the 4th? 4 a's. A to the 3rd? 3 a's. Now what? We can reduce or cancel or simplify or whatever language you like. I end up getting what? A, and it's not really necessary, but I'm going to write it a to the 1 just to emphasize this. It started out with a 4 on top and a 3 on bottom. How do you get from 4 and 3 to 1? You subtract. Right? Here's the 4, here's the 3. It became a 1. This is a to the m minus n. All right, down here, this product to a product business. This says a cubed squared. Well, the squared means I write what's in the parentheses twice. Right? And a cubed means a is written 3 times. Twice. Which gives me a to the 6th. So if you compare the 2 and the 3 at the beginning to the 6 at the end, do you see? They're multiplied, right? People confuse 1 and 3 here. Don't confuse them, but people confuse 1 and 3 often. The difference is that on number 1, both exponents have a base. Right? There are 2 base a's listed. And on number 3, we have one single base a with 2 separate exponents on that same base. Not identically linking bases, but the same base. All right. This says AB to the 4th. So AB to the 4th means I write the AB 4 times. So AB, 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 AB. And then back in multiplication, when we first define multiplication, and we do this in Math 1, but one of the properties, and you remember, it says that it doesn't matter the order of your multiplication. It's called the commutative property. That allows me to move these letters around so that it's more helpful for me to write 4 A's and 4 B's. You can move them. And 4 A's is the same thing as a to the 4th. And 4 B's is b to the 4th. And so you can see that that's actually the distributive property that we're talking about here. All right, same idea on number 5. This is A over B times A over B times A over B times A over B. We don't even need to have to compute anything, right? They just use the definition of multiplication for fractions. Multiply across the top is A to the fourth. Bottom is B to the fourth. So that's the distributed property here. Okay, number 6 requires maybe the most work, if you will. I want to rewrite this A over B as A over B to the fourth and then to the negative 1. So we already learned the A over B to the fourth on the last problem, what we did, right? On problem number 5, we just can write that as A to the fourth over B. And a negative exponent like that really means inverse. And once the inverse of this, and the the multiplicative inverse of a fraction is the reciprocal, which we learned earlier today. So I can do the reciprocal of this fraction. Right, that's what this notation means. This means do the reciprocal. And I end up with the b to the fourth over a to the fourth, thereby justifying that this is b to the m over a to the m. And here's what I want you to understand as we move to these examples. What I just did was because I want you to understand that there's reasons behind these rules. I don't want you to use the longhand way of writing things out. That's why we've got the shorthand rules. All right? So when we're looking at this next problem, these are additional properties first. This is where I want to think about. When we look at these right here, I do not want you to write out A, B, 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 B. I don't want to do that. Okay, we're not going to be writing all of this out without the exponents. We want to use the exponent properties as we get to them. All right, so there's one more slide of rules first. Do you remember what A to the 0 is? 1, and I got to show you why, because I think it's very interesting. So let's pause for a moment and see how this one works out. And it's going to look a little weird as I do this. One way of writing the number 1 is to write something divided by itself. Would you agree with me that this has the value of 1? Yeah, absolutely. But would you also agree with me that it looks a lot like rule number 2? Doesn't it? Rule number 2 had a to the m over a to the n. Now I realize that my exponents are the same on this one, but it has that same pattern, right? Exponent, a base to an exponent, same base to another exponent. So if I use rule number 2 or property number 2, this right here would be the same thing as having this. That's property number 2. What's n minus m? 0. So this is a to the 0. And if you follow the steps along, then the first one was equal to 1, the last one was equal to a to the 0, so a to the 0 and 1 have to be equal to each other. All right, this last one right here, a to the negative m, looks a lot like rule number 6. What's this one going to be? Do you remember? 1 over a to the m, right. So let's think about this a to the negative 3, and we'll do it the same way that we kind of did the last one, or the one on the last slide. I'm actually going to write a as a over 1. We're going to put it to the negative, we'll put it to the 3 and then to the negative 1. All right, so what happens when you put a power to when you put a fraction to the third power? We can distribute it, right? Okay. So a over, or a to the third, and 1 to the third is 1, so it doesn't really change anything. And then a negative exponent, or negative 1, actually means to flip it. It means do the multiplicative reciprocal, flip it. Multiplicative inverse, which is a reciprocal. So this becomes 1 over a cubed, which is actually the exact property right there with 3 involved. Okay. Example 6. We're going to write in simplest form with positive exponents. We're going to use the rules that we've been seeing. Some of them are actually properties. Some of the things we're going to use are actually properties. Others are simplification techniques. Like when you've got an A and an A and a cancel. Okay. All right. So somebody give me an example of what I could do here. There's several ways to start. What's one way I could start? Okay, so you want to cancel out 2 of these b's with 2 of those? So 2 of these b's and this 4 becomes a 2. Sure, we can do that. Now what? So what would you like to do with this a to the negative 10, Caleb? To the negative 10. You want to bring it up on top for you? Okay. So yes, that's basically that last property that we just talked about. That last property that we talked about did it the other way. It said that if you have a negative exponent, you would put it down in the denominator. But if it's already in the denominator, you bring it to the numerator. So that's one way to handle this. And this is not the only way to do the problem, but we can do this. So I have a. I have an a cubed up here now as well, and I have a b squared. Am I done? Now what do I need to do? Combine the a's, so what's that going to give me? A is 4, and that's property of exponents, right? Power of 3, power of 1. There's 4 of them. And they have exponents that are positive. Now you may have thought to do that problem differently, and if you did, that's fine. What you could have done, let me show this because I think it's important to realize. If I had started this problem, I could have flat out used the second property that says I can subtract exponents. I could have done this. I could have said a, this exponent's 1, this exponent's minus 3. Right? 1 minus negative 3. And then b, this exponent's 4, and this exponent's 2, so that's 4 minus 2. And then I could actually subtract. What's 1 minus negative 3? That's 4. So this would be a to the 4th. And then 4 minus 2 is 2. So it's b squared. Of course, you're going to get the same thing. If you didn't, the properties would be failing us now. Bad. All right, let's do one more before I quit. This one's got numbers in it. You guys like numbers. All right, so I've got 2 over 5 to the 3rd. I've got 4 over 25 to the negative 6. And I contend that I'm supposed to have the answer with positive exponents, which means multiplying this all out is not where they're wanting me to head. Are you with me? But if you take a look, 2 over 5 and 4 over 25 don't have the same representation either. They aren't the same base, right? Like I mean a and a b. But can you rewrite them so that they do have the same base? That are the same. How? Okay, so when you say reduce, what do you mean, Haley? How am I going to change 4 over 25? Say it louder, Grant. Okay, so we have the idea of a square root or representation, right? So what would the square root of 4 over 25 be? 2/5. So if I change this into 2/5, I can't just change it. That would sort of mean the problem changed entirely. What do I have to do to compensate for the fact that I just changed 4 over 25 into 2 over 5? Say it louder, Caleb. Square this. Now all of that is to the negative 6. So I took 4 over 25 and I sort of undistributed power 2. That's what I did. I really used whatever property it was of 4 or 3 or whatever I thought was 5. Property 5 in reverse. I undistributed something. And that's helpful because they both have the same base, 2 over 5 now. So we can almost be done here. This is 2/5 cubed. This is 2/5 to what power? Negative 12. Right? 2 times negative 6, that's property number 3. Property number 3 says if I have a base raised to 2 exponents, I can combine the exponents with multiplication. Now I've got the same base, 2/5 and 2/5. One of them has a power of 3, sorry, One of them has the power of 3. The other one has the power of negative 12. Now what? Add them. So what's 3 plus negative 12? Negative 9. Do I get to quit?
No.
What's wrong?
Negative exponent.
A negative exponent. So how do I change an exponent so it's no longer negative? I'll flip my fraction. So this would be 5 halves to the 9th. And I can stop there. Any questions?